Okay, so as part of the review, we had a couple AP free response questions. So you can review them kind of at your leisure. I'm just going to make video solutions, kind of explaining the process. So this first one is the 2011 question that was sort of experimental design relating to single slit diffraction. So the first part, right, we were given a list of potential equipment, and we need to figure out what we're going to use. And this might be a question where you start off with a guess, and then when you get to designing your experiment in part C, you realize you need someone else. You didn't actually need something that you checked, so you might be modifying it as you go. But the easiest thing to do is just do sort of what we've done in labs. There are multiple solutions. Most of them just make it, I think, a bit more complicated. So every demonstration that I did involved a laser pointer for a good reason, because it's a nice consistent wavelength. So my first thought would be to simply use the laser pointer. We need a light source, right? If you're going to measure a diffraction, you need something to provide light. A filament lamp is like an incandescent light bulb. It's going to provide all the wavelengths of light. So you have to do a little bit more work with it if you want to use that as your light source. I mean, you can, but you definitely need a light source. You only have two options between the laser pointer and the lamp. The laser pointer is what we have used, so I would hope that that would kind of be what would draw your eye. The second thing is that you know diffraction is based on a lot of geometric measurements, right? The distance between a slit and a screen, the spacing of the slits themselves, the distance the bright spots are apart, all that. So you need a way to measure that distance. And again, you could use a meter stick, you could use a metric ruler. Essentially, they're really the same thing. But you need something to measure distance with, because that's what we've done in the lab, and you need something to provide light, because we're trying to measure diffraction. So as long as you've checked off those things, you get 2 points for sort of your setup. So I'm going to assume that you picked a laser rather than the filament lamp approach, because the filament lamp is a bit more complicated and not really like what we've done. So for part B, we need to set up the experimental sort of apparatus that we're going to use, how it's going to be organized. And really, clarity in labeling is important. Right, so we need our light source somewhere, we need the slit we're shining it through somewhere, and we need something to project the light onto. And so, I mean, again, it should be pretty straightforward, because it's pretty close to what we've done, right? We have our laser pointer that's shining light, so we call that the laser pointer, and we have to shine it through the slit. So I'll put our It doesn't make any sense to do an experiment involving measuring the width of a single slit if we don't have the single slit for the light to go through. And then finally, we need the screen at the end to measure what happens to light, how it diffracts. Right? And that's really it. Like, that's all. You just need to sort of draw a good sketch. You don't yet need to label values and numbers. You could, if you wanted, but that's going to kind of be more in part C and D. So, experimental procedure. This is why on lab reports we have you do step-by-step procedures occasionally. That's what you want to do here. Make it clear what you're doing in the order you're doing it in. So, I'd say something like step 1, set up as in part B, right? Make that setup. 2, turn laser pointer on, right? Again, obvious, but you got to do it, right? To shine it through the slit. Then, step 3. Well, this is the part where you get some flexibility, right? You could measure a number of different things on the screen. I think it's easiest to measure the distance from the central maximum to the first bright maximum, right? So measure distance on screen using ruler from central bright spot to first bright spot. So again, the important part, I've done a couple of things in here. The first is I said, what am I using, right? I using ruler. Second, I'm being very clear on exactly what distance I'm measuring, from what point I start to what point I end at. That kind of clarity is really, really important, especially because I could have said measure from the sort of first dark spot to the second dark spot, or the first bright spot to the second bright spot, or the first bright spot on each side, how far apart they are. Any number of options, but, oh, actually, I did misspeak. I want to measure not to the first bright spot, I want to measure to like the first dark spot, the first minimum. Right, first dark spot. This is a single slit, not double slit. Right, so first dark spot. But the key is to be clear on exactly what you're measuring. And then finally, I might say measure distance from screen to slit, right? Because I know what's going to be involved in determining the slit width. And I know I need that sort of screen to slit distance as well. And that's really all you need. You don't need to be perfect about it. But something like that would cover all the details. That's basically what we've done in lab settings as well. So now we have our procedure. And we need to detail sort of the calculations that we are going to make. And so it depends a little bit on exactly what measurements you told them to take, right? If you're saying measure the distance between two dark spots, that's a different calculation than if it's between the center to the first dark spot or something like that. But I'm going to say we use the procedure I did. So from the central bright spot to the first dark spot. And so what we have on the equation sheet is m lambda equals d sine theta. So we need to figure out how to turn this into sort of exactly what we measured and make sure all our variables go in the right spots. So, first thing to note is we said from the central maximum to the first bright spot. So m, this is just 1, right? Again, if you pick something different, m might have a different value, but that's okay. For me, it's just 1. The next thing is we got to figure out what to do with sine theta. We know from geometry, tan theta is the distance we measured, which I'm going to call delta x, over the distance from the slit to the screen, L, right? So I'm going to put that actually in my procedure. This is delta x, and that is L. That way it's very clear what distances are what, because there's distances, right? And so, depending on whether you're comfortable calling this a small angle or not, you could say, quite correctly, that for small angles, sine theta is about equal to tan theta. And then you could substitute there. Or you could write both these relationships independently and show how you'd calculate them. I think it's a reasonable assumption for a small angle, so I'm going to do that. So this turns our equation into lambda equals d, which is the slit size, delta x over L. Right? So now we just rearrange, right? Lambda L over delta x equals d. And this is the slit width. And again, so if you measured from dark spot to dark spot, you would get a factor of 2, right? If you measured dark spot to dark spot, it'd be like that. We didn't do that. I specified exactly what delta x is, so we don't have that ambiguity. And so this should determine your slit width. And since it's saying explain, you should probably write a little bit. A lot of what I've talked through, I didn't put everything on here because it's a pain to write. So talk through sort of the assumptions you're making, why you're doing it, and so on. Okay? So that's part D. So part E is another sort of descriptive stuff. We increase the separation of the strips, or rather, we make the slit wider. We keep everything else the same. What are we going to do? Well, we have from the previous slide, right, we have D equals lambda L over delta X. So delta X is our slit spacing. If we make D bigger, then this side of the equation has to get bigger, or delta X has to get smaller, right? And so, because they're inversely related, the fringes get closer together, or the central maximum gets narrower. And that's really all you need to say, right? This, recognizing that this is an inverse relationship, and that an inverse relationship means widening the slit makes the fringes closer together, then you're done. Just those sort of two-sentence statements, whether it's an equation the way I did it here, or writing it. And that's it.